On October 13th of 2016, the Nathan E. Stewart, an American-owned tug, ran aground in Heldsick territory on the central coast of British Columbia after its watchperson fell asleep. As the tug sank, it leaked more than 100,000 liters of diesel fuel, lubricants, and other pollutants into the surrounding waters. And the ocean carried these pollutants like a massive conveyor belt, affecting a huge swath of the local fishing waters. One tool that could be helpful in emergencies: a model of the ocean itself. A numerical ocean model is a set of mathematical equations that can predict how waters will ebb and flow hours and days from now. Fisheries and Oceans Canada has been working with numerical models since the 1970s. Back in 2016, when the Nathan E. Stewart ran aground, they had already modeled ocean currents for both the southern and northern coasts of British Columbia, but there was a gap in the middle.
It was clear that there was a need for some high-resolution modeling in the Central Coast, but we didn't have the capacity to do it. And it occurred to me that with Hakai's work on the Central Coast, that there was an opportunity there.
Hakai oceanographer Pramod Thupaki took up the challenge and has created a numerical model for the Central Coast of British Columbia. And the applications of this work are vast. All sorts of groups can use the predictive power of the ocean model. It helps biologists predict where baby organisms from seaweeds to sea stars drift before they settle. It helps the aquaculture industry minimize their environmental impact and optimally use farm area. It helps researchers study the amount of fresh water that enters the ocean from streams and rivers to predict the impacts of climate change. By dialing up or down the flow from rain and glacier melt-fed rivers, they can investigate how the digital ocean will react in possible future conditions. And then there's the more emergent applications, which takes us back to the Nathan E. Stewart disaster. Our vision is to help coastal communities be better prepared if another disaster strikes, when every hour counts.
Accidents in the ocean happen in usually the worst conditions and in really remote places where it is really important to optimize where you place these crews and where you send the response teams.
And so you can use these models to build up an understanding of what kind of things are likely to happen, so then you can build yourself an emergency response system which has some hope of being prepared for the likely scenarios.
To prepare for that next emergency, the model needs as much oceanographic data as it can get. It depends on data coming in from across the Hakai Institute, as well as from Fisheries and Oceans Canada, Environment Canada, and the Canadian Hydrographic Service.
Numerical ocean models can be used to set up different conditions and different processes. What keeps it honest and what keeps it close to reality are all the observations that go into it. The more detailed, more comprehensive the model is, the more accurate it can be and the more useful it can be.
There are 3 variables that the model uses to predict currents: temperature, salinity, and velocity in the water column. Our science team drops instruments to gather data on temperature and salinity. Velocity, though, requires an even more advanced tool: ADCPs. They use the same principle to tell how fast the water is moving that police use to clock passing cars on a highway. That principle? The Doppler effect. The ADCPs use sound to measure velocity, but they do so underwater by listening to the frequency change of the echo as chirps bounce off suspended particles. And then all the data is fed into the model.
You can easily use hundreds to 1,000 computers to actually run these simulations. And it can take these large computers hours to days to run.
By visiting this address, you can check out the model yourself.
There are no boundaries in the ocean. In the global context, things that are being dumped into the ocean, a world away from you, might be affecting how you experience the coastline around you. The only way we can actually look at conditions or try to predict conditions is using these models, and that is such a powerful tool that has always drawn me to that.